All right, guys. We did the first couple. We did this one, right? Did we do this one? Yes. Did we do this one? No. Okay. Determine when. When is time, right? That's the piece you're looking for. Your investment, you want it to accumulate to be this much. You want to earn interest at a rate of 8. You want to be able to graph this. You want to be able to look in quadrant 1 and see this. Your exponential and your constant. You want to see where they cross. It makes a lot of sense if you go look at the table. Look at the table because you're looking to see when does your money reach this. Because that's the constant that will be all the way down your Y2. You're going to look for your Y1 to get to be that much money. Granted, it's not going to be exactly, but you'll be able to see like between 11 and 12, oh, I get that much money. So it gives you a good feeling when you look at your table. I think it's easier to look there. And then do your intersect because it gives you a good idea. Yes?
You just said that we could put 12, right?
You could put what?
12 years. Just said that.
No, 3 decimals. Money is 2 decimals. 3 decimals. Okay. Any questions? You tell me where your questions are. 4. Okay. Let's take a look at what 4 looks like. So, when my investment doubles, I don't know, pick an investment. What's a good amount to invest? 100. I'll invest $100. What do I get when it doubles? $200. I want it quiet. So if I start like this, whatever that happens to be, and I divide by 100, what does it become? 2 to 1, doesn't it? If I invest 500, and it becomes 1,000, and I divide by 500, remember, this belongs only to the E, not the 100. Aaron. And I divide by 500, what do I get? 2 to 1. So I can invest $1 and make it $2. Just keep it as it doubles, 2 to 1. What if I triple my money? What would it be? 3 to 1. Yeah. If I double my money, 2 to 1. If I triple my money, 3 to 1. Pick any number you like. When you divide that through, because remember, this piece only belongs to the E. It's right next to the exponent. If I gave you this, and I asked you what the exponent is for 3, what would you tell me? What's the exponent on 3? 1. It's not 2, right? It doesn't belong that one. It only belongs to this guy, this guy. This guy has its own. Everybody gets its own. Even though they are factors and I'm multiplying, they have their own exponent. Same thing happens here. This only belongs to the E. It's being multiplied by P. So divide the P out of there and break it down to a double. And the rest of it kind of works nicely. It also works a little bit better on your graph if you're doing a 2 to 1. You don't have to change too much of your graph. You can almost do a standard graph and bring it down to quadrant 1. Just put your x min and your y min at 0. Remember to do this. This is important. And remember when you're doing an exponential curve, this is the whole curve. This is the way it looks when you do it across the four quadrants. We don't want this piece nor this piece. We can't have negative time. We're not going to have negative money. So we're only in quadrant 1. So while this is a complete graph, this is called a situational graph. It represents my situation. So I can only exist really in quadrant 1. Make sense? For the rest of it, we saw the exact same way. Okay? Okay. All right, number 5. We did number 5. We did with the interest rate. Number 6. Again, number 6 is just like number 5. We're determining the annual interest rate. Annual means I'm compounding 1. one time. Monthly means I'm compounding 12. You do your compounding monthly, sorry. You're determining at the end of this year, what was my interest rate? What did I use? So the R is missing. Now, when we do this, you cannot distribute this over here and get that out. This belongs to this one, which is what makes it a little bit hard to work with here. So, therefore, graph this and take a look at where your graph intersects. Now, we said yesterday that your rate, your X value, is your rate now. This is my rate. My rate goes percents, 3%, 2%, 5%, 9%. But I move it like this when I calculate it. So if this is my 0, you might want to go like by 0.05, by 0.01s, whatever it is you want to go by, make it easier to see. And this one was a little higher than the 0.10, so you might have to go a little bit higher. You'll see that they didn't intersect yet when you do this. If you left it, remember what we did yesterday, we left it so that it kind of rode along here, but you couldn't see it. It could still do an intersect. Your calculator will still do an intersect with that. You just can't see it because it's sitting right along your axis because you left your scale too low. That's the only difference. And if you want to leave it as a decimal or you want to move it to a percent, just move it over 2 decimal places. Sound good? How many of you were able to get this one? Yeah? Good. It was just like number 5. The rate is always a little trickier because it is so small. Number 7, how much time, T, to double? Again, we're doubling. I did the 2 to 1. You could do 100, you make 200. 500, you make 1,000. You're going to divide that out anyway because this exponent only belongs to this piece. Whenever your variable is in your exponent, the only way to get that variable down algebraically is a log. However, if we graph it, because we can graph your exponential curves, we can see where they intersect. And that's like the goal for your exponential functions, is to be able to graph them. Give me 3 decimal places on your years, your time, your rates. I need money, 2 decimal places, because that's what we normally pay to, is the 2 decimal place money. Questions? You good? Okay. And this one, again, I like this one. It's a little bit tedious, but in your calculator, you just bring it second down and change whatever piece you need to change. This said, Sally's going to invest, God bless you, $500. And she's going to invest it at a flat rate of 6%. That's not going to change either. Assume that she just leaves her money in there. After 5 years, how much does she have if we change your compounding times? So this is a nice way to keep everything else the same and just change one variable. Remember, whenever you're looking to see the difference in something, you want to just change one of those variables. You don't want to change more than one because then you don't know which one had the effect on it. Change one variable at a time. So in this case, we're changing our compounds. In the other homework that we did from the other night, we also changed our time and we kept everything else the same. I think we did a PERT or an annual. We just changed time. You only should do one variable change at a time if you want to see where the difference is. And we said that your daily is the closest to your compounds continuously. That's going to be your closest one because the formula for that is very, very close to your continuously. Your continuously is the one that uses PERT. And that's about the closest you're going to get in your compound daily. I mean, it would be nice if they put the total interest over and over again. Remember that that 1 plus rolls that interest back in. The bank doesn't have to have somebody there adding it back in. It rolls it in by doing 1 plus. That's 100% plus whatever interest it gained. Questions? You're okay with these? These are great interest programs, interest formulas. All right. Let's, the fact that your basic basic formula works like this. Put this at the top of this page. This is any type of exponential curve where A is your initial value, B is going to be your rate of change, and X is going to be your time. Your principal and interest followed the same pattern. It did this. P, that was my initial investment, rate of change, here was my rate in here, and here was my time out here. It follows the same way. If I did a decrease, I did a 1 minus something. So when we do this, we're going to keep this, and B is going to be our rate. Now, if we're doubling, if we double, B is the rate. If we double, then B is going to be 2. If we triple, what should B become? 3. If we do a half-life, what do you think B would be? 1/2. I'm taking half each time, right? So that's going to be our rate of change, is what the B is. Now, sometimes we have a population increase of like 3%, 2%, a decrease, 2%, 1%. If we have something where the percentage changes, then B, for an increase, will be 1 plus R, whatever the rate of change happens to be. We're still talking about your rate. If we have a decrease, it's going to be 1 minus R. I should see this somewhere on your paper. Put these down. Another problem we have is we understand what our initial value is. That's pretty straightforward in most of these formulas. But time is a little bit different. The value of time changes a little bit. Sometimes we have a cycle of time. Like for instance, in this problem, your bacteria is going to triple every 4 days, not every day. So I can't do it to the X and say every day my bacteria will triple. I want it to triple every 4 days. So we have to set a cycle. And we set our time over our cycle. So if I'm going every 4 days, my time is going to say days, I don't know, every 4. So if it's 12 days, it has tripled 3 times every 4 days. The 4th day, the 8th day, the 12th day. Does that make sense? Sometimes time has a cycle. Things don't double or take half, like a half-life of a chemical or something that you learn about in science, right? When you do a half-life, it's usually like how many years or how many days. If it's an element, it's like every 28 days, I'm going to take half of it. So you can't put X in there because it would go every day, take half of it. So we do X divided by 28. So for 28 days, I took a decrease. For 56 days, I decreased again. Every 28 days, that would make that cycle go through. So we're going to see these types of things. And A is going to be what you start with initially, the initial amount. Y is what we end up with, our resulting amount. They all follow basically the same type of format. Your interest rates did, and these also do. So kind of like gear yourself to that one. So let's take an example here and see what this looks like.
What was the Y again?
The Y is what results. Okay, we have a situation. We have the number of bacteria triples every 4 days. This piece right here is my time. Every 4 days. My time is going to be in days, but I'm tripling every 4 days. So I can't raise it to the X. That says days. So my time cycle is going to be X over 4. So if you think about it, in 4 days, I triple. In 8 days, I triple again. In 12 days, I triple again. every 4 days, I will triple. Initially, I start with 1,000 units of bacteria. We want to know how much bacteria is present in 4 days, 8 days, 12 days, 9 days, 1 day. How much bacteria will be present? My bacteria is growing. It's increasing, right? And I want it to triple. This is my rate. So we start here with the basic formula. What is my A? What's my rate of change? 3, because I'm tripling, right? Tripling. And my time says, my time is in days. If I wrote just plain X, that means I'm tripling day 1, day 2, day 3. I'm tripling every day. But I want to triple every 4 days. So my time cycle is X over 4. Now, take your calculator and plug this into your Y equals. Be careful when you raise that value to the X over 4. If you have the old software, that has to be in parentheses. In other words, if you put it in like this has to have parentheses around it. Order of operation knows that this is an exponent first, okay? Let's see if we can figure out where we should set our window so we can actually see this thing grow. What quadrant should we be in? 1. So automatically your X min and your Y min are at 0. Start by setting your window to that. Now, I put out some of the table here so we can see what's happening. At the beginning, this is my initial, I start with 1,000 units of bacteria, whatever you call these units, I guess. Pieces, cells of bacteria. Now, on day 1, did I triple this on day 1? No. I said every 4 days. So on day 4, was this 1,000 times 3? Okay. Day 8, another 4 days. Was this 3,000 times 3? I'm tripling. On day 9, was this every 4? Day 12, every 4. I'm taking my 9,000 times 3. Got a lot of bacteria cells going on after 12 days, right? This is my exponential growth. So in your calculator, this is a good table to help you. We only need to go up to 12 days. So your X can go from like 0 to, you can make it go 15. And your Y, what should Y be set at? 0 to what? 28,000, 30,000. Doesn't matter what we set it, as long as it's higher than this and I can kind of see it on my chart. Even though you can't see any other part of your graph, you can always see it in your table. So if you struggle with how do I set my window, look at your table, right? So we should be able to see your graph increasing. Here's my 1,000 that it starts at, and it keeps increasing. Now we can tell right by your table what this is. I can tell my 0 days initially. I could tell my 4 days. I could see my 8 days. I could see my 12 days, my 9 days, my 1 day. And remember, even if you don't see it on your table, if I say 1.5 days, if I say, tell me what happens after 1.5 days, do a value on this second calc value and put in your value for 1.5. And you'll tell how many grew in 1.5 days. So this shows growth of bacteria. Make sense? All right, let's take a look at another problem. Oh, what's going on here? start with your very, very simple formula. Anytime you do an exponential, we're basically looking like this, AB to the x. Now, a population is decreasing by 2.5% a year. Let's first take that percent and turn it into a decimal. What would my decimal be for this percent? 0.025. Same rule, move it 2 positions. The initial population starts at 1,000. My population is going to decrease 2.5% each year. It's not at a flat rate because your amount's going to change each year of how much is left. I want to know what time will this be, how much time before my population reaches 95,000. Now, notice I put decrease, increase. This is your A, B to the X. This is when we're using a decrease. We're starting out with a population of 100,000. We're decreasing it each year by 2.5%, 0.025. Now, remember, when we talked about the decrease, we said you're actually getting what is left. So if I subtract 1 minus 0.025, there's my 0.975. I got 0.975%, or 0.975 of my population left each year. And I don't know how long this will take me. There's no cycle to this. And I want to know, when do I end up with 95,000? Again, my variable is my exponent. Algebraically, we need a log to solve this. So we're going to use the graph. So we're going to go to our graph. We're going to put y1, y2. Let's talk your window for a second here. X and y min both start at zeros. What should my y max be? I'm sorry? My y max. I should start at 0 because I have to be in quadrant 1. I have no negative population. What max y should I put in there for me to see my graph? 100,000. If I'm going to start at 100,000 and keep going down, right? So I'm never going to get higher than this because my population is decreasing. No comma. My x represents what part of this equation? What's my x variable represent? Time. Time in days, years, each year. How many is this going to be? Days, years, months? What does my time represent?
Year.
Year. Good. Each year. So, what can I make my x value go to? It sounds reasonable. 10. I can take a look at 10. If I don't see them cross, what do? I change it. I double it. Good rule of thumb. So you're going to graph this, and you're going to take a look at your graph. This time around, you're going to see a decreasing one. He's decreasing. Started at 100,000, decreasing. Okay? And where it hooks up to your 95,000 is where you're going to do your intercept and find out how long did it take to get down that far. And we really weren't reducing too far down. So you're going to do an intercept and give me your x to 3 decimal places. And this again, time is in years. So anybody come up with one? 2.025 years. Okay? So it's not taking that long for me to get my population to decrease at 2.5% a year. It was really not a very big steep decrease. Right? What this does right here is say, when I subtract this from 1, it keeps this percentage, 97.5% of your population, it retains. It lets the 2.5 go and retains 97.5%, is what the decrease does. Okay? Do we have time for one more? I know you're going to say no anyway.
We really don't.
Okay, just let me do a half. Let me set up a half life. Let me set up a half life. You have 2 minutes.
No, we don't have a minute now.
You have 2 minutes.
All right.
Okay, we start like this. All right, initially there are 4 grams. We don't know the initial amount. There are 4 grams after 10 days. Your half-life is 12 days. There's your cycle. B is your 1/2. We don't know your A, but we know you end up with 4 grams after 10 days. 10 is your time. So you can figure this piece out, divide that, and calculate A. That one wasn't too long. Okay, so for homework, how many are on this? Let's see. There's 8. All right. 8's not so bad. Okay, that's your homework task, guys.